Okay, I think we should be able to start. Rick, do you want to give some introductory words?
Yes, I can do that. Sure. So, well, so it's my pleasure to introduce Loes Crielaard today for the presentation. Loes is working in the public health department in the AMC, so the medical center in Amsterdam. And what she's working on is trying to translate expert knowledge into computational models. And that's a very hard thing to do. And there are some other people also in the IAS doing similar things, but on different domains, namely Jeroen and Bas specifically for this work. And so what we thought about, well, I think already something like 2 years ago or so, is, well, can we take the things that we learn from our experiences and best practices and put them in one kind of framework and help others do basically the same. Well, without, of course, giving too much detail away from Loes, and should also apologize, I guess, for Bas. So Bas was also supposed to be presenting or helping the presentation, but he fell ill, unfortunately, so he cannot be here. And the reason that I'm introducing Loes is that also the chairperson is ill, so I guess there must be some kind of epidemic. In any case, without further ado, Loes, I would suggest you take the floor.
Thank you, Rick. I think now you can see my entire screen. So today I will present this work that we've been working on for a while now, together with colleagues who are doing similar things. Well, Rick just explained it all, so that's good. And this methodology paper that we've been working on, we have humbly called Refining the Causal Loop Diagram. And what we describe in this paper is a tutorial for maximizing the contribution of domain expertise in computational system dynamics modeling. So as you all know, complexity science studies the way in which large groups of individual components behave collectively by adapting to each other and the environment they create themselves. It has historically been closely tied to mathematics and physics. However, over the past 2 decades, the need for embracing complexity science to study problems in biopsychosocial domains has become apparent. And many people have agreed that complexity science is a relevant paradigm to study prevailing problems where biology, psychology, and socio-environmental factors interact. So some examples of this where this has been applied are mental health and more specifically depression, public health and the obesity epidemic, planetary health and climate change, and social dynamics and polarization. So complexity science aims to model the spatio-temporal dynamics of a system to explore its inherent patterns. And this usually starts with developing a conceptual model. And such a model makes causal hypotheses, knowledge, and assumptions concerning the system of interest explicit. So it can be seen as our understanding of how a certain system works. And one way to develop a conceptual model is in the form of a causal loop diagram. And this has become very prevalent over the past years. And a causal loop diagram does these things. So makes causal hypotheses, knowledge, and assumptions explicit. It's a visual representation of how a certain system works. And it's very versatile in that it's quite intuitive to understand. So therefore, it's a medium that is applicable when you're working with different experts from a lot of different domains, which is of course relevant if we're talking about these giant problems such as the obesity epidemic. And here you see such a causal loop diagram that was developed by Jeroen and colleagues for Alzheimer's disease. And while a causal loop diagram, as you can see, contains a tremendous amount of information, and it's also a great way to unravel causal mechanisms, you can kind of deduce from this picture that human brains are generally not reliable in predicting the long-term effects of interconnectedness, feedback loops, and nonlinearities. So even though we now have this beautiful conceptual model, there is no way for us to know what would happen if a variable on the left-hand side of the model would shift a little bit, what would happen on the right side of the model. So therefore, complexity science is also closely related to simulation-based science. And this takes the conceptual model and transforms it into a computational model. So a computational model is a quantified adaptation of the conceptual model, which you can implement on a computer and run experiments and simulations with. However, the application of computational models after developing a conceptual model is less prevalent in the biopsychosocial domains. And this may be attributed to the infeasibility of experimental research in these domains, as well as the difficulty to obtain rich data. You can imagine that even though collecting longitudinal data on human societies is becoming much more widespread, it's not feasible to get data that are as comprehensive and accurate on these systems as would be obtainable in fields such as engineering or physics. And this is related to the cost and feasibility of collecting data on human systems. For instance, that's due to rapid changes in the underlying system, relevant variables on many spatial and temporal scales, the difficulty to replicate a controlled environment, and unclear system boundaries. However, this is problematic because usually experimental data as well as observational data on systems are important building blocks for developing a computational model from the conceptual model. But still, we would like to develop these computational models as a second step after a conceptual model, because they are necessary if we want to explore and interpret and manipulate in silico the emerging dynamics of a system. So then I've described our knowledge gap. So there's a need to identify methods to build computational models from conceptual models using the sparse available data in the biopsychosocial domains. And currently, a lot of causal loop diagrams that are developed have the final aim to be a conceptual model. So therefore, we noted that protocols to develop causal loop diagram lack steps that would allow for subsequent conversion to a validated executable computational model. So here you see such a current state of the art CLD. And you see that the information included in here consists of variables. You see 4 of them, and causal links in the form of arrows, which are accompanied by a polarity, either plus or minus, where plus means that if one variable increases, then the other variable increases as well. Minus means one variable increases, the other one decreases. And you also see feedback loops identified here, one reinforcing feedback loop and one balancing feedback loop. So this is the information in a causal loop diagram. So what we propose here, and what Rick just said as well, is that we think that we could ask the experts for more information about the system than that information that's currently contained in a causal loop diagram, such that it could subsequently be converted to a computational model. So the paper describes steps that can contribute to this. And for this, as Rick said as well, we draw on the experience of the Institute for Advanced Study community, because there's a lot of expertise here with converting mental models of experts to simulation models. And the focus in our paper is on causal loop diagrams as conceptual models for all the reasons that I just described. So They are now popular, that's important, and also they are very versatile, easy to understand, intuitive. And we focus on system dynamics models as computational models, which I will get to in the next slide. So for reasons that you will now understand, in this paper, we propose the annotated causal loop diagram. So the paper is called Refining the Causal Loop Diagram, and this is then the refined causal loop diagram that we suggest, which is more annotated than just the information that is contained in the current state of the art causal loop diagram. So a systems dynamics model, which you want to then convert your causal loop diagram to, consists of a coupled set of differential or difference equations. And already the founding father of system dynamics modeling said that this is an intuitive computational implementation of expert knowledge combined with data. You can also say that it has the minimum amount of mathematics necessary to convert your conceptual model to a computational model. And what's also cool about system dynamics models is that the architecture can incorporate other computational models, which may lead to a modular construction of a multi-scale model. So, for example, in theory, you could have one variable in a system dynamics model, for instance, be representative of social capital. And then in theory, have not tried this, but you could have an agent-based model that actually feeds into the system dynamics model that determines this social capital. And here you see the modeling and simulation cycle, and I want to show this so that you get a feeling of actually the difference between a conceptual model and a computational model. So on the left, you see you have an observed phenomenon, and via qualitative modeling fed by theory, you can develop such a conceptual model. On the top, you can already see that with such a conceptual model or a causal loop diagram, you can already do many things. But if you want to go to the simulation step that you see below, you have to go to the quantitative modeling and the system dynamics model. So Bas, he's not here, but he wanted me to call this slide a causal loop diagram about the paper about causal loop diagrams. So this shows our workflow that we describe in this paper. And today I'm going to focus on the left-hand side of this workflow because it's the most novel thing that we propose. So first, I want to talk about how domain experts and knowledge could contribute to formulating variables that could be captured in a scale separation map. And for that, first we need to go to the basics, the research question and the context of validity. So as many of you know probably, any model is only valid in a predetermined context of validity, including spatial and temporal scales, and a research question agreed upon by experts. Even though that sounds quite obvious, this is very important to realize before you start the model building process. So this person said it beautifully, I think. The purpose of the computational model provides the anchor. And so if you, before you start the model building process, which thus starts with developing the conceptual model, the causal loop diagram, you need to define this research question and context of validity. Otherwise, there's no defined boundary to accept or reject proposed variables and causal links. So you have the fear that your conceptual model will include the whole world. No, but you have to confine it. Otherwise, if you don't do this before you start the model building process, the result will be a mix of model components for a set of different contexts, while not valid for any of them. And therefore, a model should never be used outside of the context for which it was developed without careful consideration and enhancement. This maybe sounds a bit abstract, so I included an example. Imagine that we have a system dynamics model based on a conceptual causal loop diagram that is about the physiology of overweight in an individual. So it describes this individual's physical activity level and his or her total daily energy intake, and it wants to see how an energy imbalance in this person resulting from those two factors over a scale of months could contribute to overweight in this individual. Then we cannot use this model as it is to look at a research question which wants to discuss the influence of the local built environment on overweight. Local built environment has changed over the last 50 years to include this more junk food availability, for instance. And if we want to look at this macro level over a scale of years, we need to include many more variables than we just had if we just wanted to look over months within an individual at this physiological energy imbalance. The second annotation is documenting authorship. And this sounds as if it was already clear, but it's very important to realize that aCLD is a reflection of the knowledge and assumptions held by a person or a group. It's thus a shared mental model. So a true conceptual model or causal loop diagram about a certain system does not exist. The causal loop diagram is intimately tied to the group of people that developed it. Very often now a causal loop diagram is developed using group model building. This is a participatory modeling technique in which the goals are knowledge elicitation from a group of experts, but also reaching consensus among this group of experts. Yeah, so put the quote here, all models are wrong. So this aCLD should really be seen as a reflection of the collective understanding of a specific group of experts, which is systematically collected, and then the consequences are calculated in using a system dynamics model. It does not reflect the truth. And to have a shared mental model that is as comprehensive as it could be, it's suggested to have an expert group that develops this shared mental model together that is diverse yet overlapping in their domains. So for example, if I'm public health and I'm building a model with one immunologist, I would rather have actually two immunologists, because it is not worth that much if I agree with the immunologist because I have no idea what she's talking about. So it's more about that two immunologists could discuss together such that the consensus is actually worth something. And we suggest that this could be proven, this diverse yet overlapping selection of domains by including an expert domain cross table with the causal loop diagram, such that so that would entail having on the rows all the different experts, and then on the columns the different domains of expertise, where you want preferably every domain to be represented by at least two experts. Then we go to variable selection and the skill separation map. So you want your experts to tell you which variables are important in modeling this system. And these variables can then be grouped along a skill separation map. Here on the left, you see an example of a skill separation map. So on one axis, it has the temporal scale on which a variable acts, and on the other, the spatial scale. And this is actually important to use this expert knowledge about these scales, because later when you build the computational model, you want variables on a smaller temporal scale to average out. So for instance, on the left, you see skill separation map that corresponds to a model looking at overweight and social norms towards body weight. And here, for example, physical activity level, if you want to look at this system over a scale of months, maybe can be averaged out over weeks. You don't need to know what the physical activity level exactly is every day of this individual. And variables that act on a larger temporal scale can be kept constant. So for instance, here you see age and height. If I want to look at something that changes on a temporal scale of months, probably the influence of age and height on weight and social norms towards body weight can be kept constant here. It's important in this variable selection phase that the variables are defined unambiguously. So for example, here you see on the left total daily energy intake, which is probably not what an expert would actually say. They would probably say physical activity level. However, I cannot talk about, if you imagine, if you think back to the causal loop diagram example that I showed you, where you have the pluses and the minuses, I cannot talk about more diet. I need to know exactly what it is that becomes more, that has this effect on weight. And also variables need to be defined neutrally. So it's very tempting, for instance, if you have this model about overweight and social norms, to talk about an unhealthy ideal BMI, for instance. But actually, you should just talk about an ideal BMI, because you cannot have a higher or lower unhealthy ideal BMI. Okay, then we go to the next block, which is about the annotations that we propose for the causal loop diagram, such that it is then an annotated causal loop diagram. And to explain that, I first have to introduce you to uncertainty in modeling. And here specifically want to talk about structural uncertainty, which is about the uncertainty about the topology of the aCLD and equations used in the system dynamics model. And this leads to uncertainties in the corresponding simulation results. If these uncertainties in the topology of the aCLD are simply ignored or decided one way or another, this creates bias, overstates predictive power, and may lead to wrong conclusions. So, for example, if we are not clear about that we are uncertain about a certain part of our shared mental model, then we kind of pretend that actually we are sure, because that's what we then need to assume. And therefore, this creates these wrong conclusions. So the next annotations that we discuss are all about making these uncertainties explicit and annotated in the aCLD during conceptual modeling. And a long time ago, it was already recognized that this structural uncertainty about a causal loop diagram or conceptual model can be reduced by maximizing the domain knowledge used in development, which is exactly what we want to do here. And we provide some suggestions of how you could do that. And this, I just want to show you this again for illustration. So imagine that you make a mistake have an uncertainty in the conceptual modeling phase, then this propagates through the whole modeling and simulation cycle. First, recording consensus. If a CLD is the result of consensus between experts, as I said before, it makes it more comprehensive and more certain. So it strengthens the certainty regarding its structure. But conversely, disagreement among experts increases structural uncertainty. So if one expert says this link should be there and another one says, no, I don't agree, it shouldn't be there, then this link is actually an uncertain causal link. And in theory, we should then account for all the multiple possible models that could be the result of this uncertain causal link. So we should calculate the consequences of a link of conceptual model that either includes or does not include this link. One way to look at this is that if a link is uncertain, so one expert said it should be there, another says it should not be there, you could vote. So ask the rest of the group whether they think that causal link should be there or not. that can then be used as a measure of certainty for the existence of an uncertain causal link, so a prior probability, to give us a bit more certainty about the uncertain causal link. Related to this, we propose to record known to be absent causal links. So these are links that we know are not a direct cause of effect. It sounds a bit strange because in the causal loop diagram, you actually wanted to capture how we thought the system worked. So why do we have to think about the things that are not there? But this is also to reduce the uncertainty. So if at the moment, if a causal link is not present in the causal loop diagram, it remains unrecorded whether this is because this link is known to be unknown. So that's the case what I talked about before. So two experts disagree, we don't know. So therefore it should actually not be excluded. Both cases should be accounted for. Whether this link is unknown to be unknown, we just never discussed whether this link could be there or not, or it's known to be absent. So it can be that two experts, that the group of experts discussed whether a certain link is there or not. And then they said, no, that we know that link is definitely not there. And if they would write that down, then that would mean that as a modeler, you could cross that option off your list. So you could be sure that you don't have to search there in the model space. It's not a possible structure of the conceptual model. However, if we assume that an unrecorded causal link is known to be absent, so that's, I think, what most people are doing now. If a causal link is not there in a causal loop diagram, we think, okay, that must mean we know it's not there. But then we underestimate the structural uncertainty because we don't know if it's really not there or if we just don't know. So what we suggest is that adding the annotation of known to be absent causal links, so really the options that we can cross off, enables bringing the structural uncertainty to a manageable level while reducing bias. Related to this, we suggest to record intermediary variables. So sounds obvious, but only direct causal links should be added to the causal loop diagram relative to all variables included in the aCLD. So if a new causal link is proposed between two variables, should discuss among the group of experts whether this link actually should be rewired via one of the other variables that's inside the model, because this mediates the causal relationship. And this also has another side, which is that if you don't record these mediators, and actually mediators do overlap between different causal relationships, it has to be assumed that the intermediary variables underlying the causal links are independent. So here you see an example of this. For instance, if we have the experts have come up with the model on the left, where physical activity level leads to self-esteem and healthy diet has an effect on snoring. If they would not reason about which mediators lie underneath these causal relationships, it would not become clear that actually these two processes are correlated, because they are both mediated by the variable weight, which is very important for the next computational modeling phase. We also think that the experts could be, their expertise could be used in describing the functional form of causal links. So the functional form of the mathematical, of the causal link is the mathematical equation that best describes the causal relationship. And that refines the initial polarity used for a causal link. So now I showed you that in a state-of-the-art causal loop diagram, you have links accompanied by a plus or links accompanied by a minus. But that doesn't really tell you how this effect comes into being. If one variable increases, the other variable increases as well. This can be in a lot of different ways. Is this linear? Is this exponential? We don't know. So as if you were the modeler then and you only have this plus, you have to look at all the different relationships that could be related to this plus. So we suggest that experts could be asked to draw a selection of mathematical relationships for experts to choose from. And this is related to, well, in the same spirit as what I discussed before, if there are already some options that we can cross off, that the experts say, it's definitely not this, it's definitely not this functional form, then this already decreases the search space. Then we also suggest to describe interaction terms. Currently, there's no format, as far as we know, for that in the current causal loop diagrams. We usually discuss causal loop diagrams where a variable is connected to another variable by one causal link, but actually there could also be relationships that are a many-to-one causal link, as opposed to a one-to-one causal link, in which multiple variables collectively bring about a change in another variable. So this is interaction, and this could be recorded as well. So an example of this is the logical AND gate and a logical OR gate, as you see over here. So you see that the AND gate represents that both variables A and B should be present to bring about an effect in variable Z. And the OR gate shows that either A or B should be present to bring about a change in variable Z. And then lastly, providing high quality literature evidence. Empirical evidence for a causal loop diagram is often provided implicitly because a lot of different models are, a lot of different causal loop diagrams are based on literature. But we suggest that this should be explicitly specified for each different variable, and each causal link should be specified, and in which what the specific literature is that is connected to that element of the causal loop diagram. This allows for iterative development. For instance, if there was one causal link included in the causal loop diagram because the experts thought that this causal link was there, but then afterwards a randomized control trial comes and says this link is not there, then we can actually see what evidence the inclusion of that link was based on, and this can be overturned. This also provides a concrete basis for discussion among experts. So in the same way, if one expert says this link is there, I think it really is there, and another says this link is not there and I have evidence to show it, then this evidence can be the deciding factor for this discussion. Although, a side note here, if an expert suggests a link and we don't, it's just not reported in literature, then we still think it should be included, because primarily a causal loop diagram is this reflection of the shared mental model of a group of experts, what we discussed in the beginning. So that was the left side of the model. So just some very brief words about the right side of the model. I'm not discussing that today because you can already see what time it is. And also because these steps have been described before, maybe not in combination, but they have been described before. The paper describes really the process from A to Z, but yeah, so here you see that we also include a validation step, as well as uncertainty quantification and sensitivity analyses, which are not often performed in this context of system dynamics modeling. And then the final goal of this is scenario testing, or exploring what if scenarios. So the idea, this is Bas' slide. The idea is that you can test what if scenarios, which was exactly the point of going from a conceptual model to a computational model. to test the effects of hypothetical interventions and quantify causal pathways, which you all could not achieve by stopping at causal loop diagram. That's it. Thank you very much.
Thank you. Digital applause. All right, so I open the floor to questions. Or I'm not, Fabian, I'm not sure if I was taking over.
No, you're doing a great job.
Oh, thanks. Well, you're the one sitting in IAS. So I open the floor for questions. Anyone from the audience, either put it in a chat or just unmute yourself and start talking. Vitor.
Can you hear me now?
Now I can hear you. Yeah.
Yes, great. Thanks for the great talk. I think it was very clear. And I have a simple question that I guess I could try to read the paper first, but since you're here, it's easier just to ask. I was wondering about these annotations. Do you suggest any of them to be directly on the diagram? Like, do you have some notations for how to do that or anything like this? Or do you see it as like a side thing that you keep with the diagrams?
So we have suggested a format for this, although it's not set in stone, of course. The skill separation map and the expert cross table that we talked about would, of course, be separate, and also would suggest that you include a table separately that describes the literature related to each causal link. But for instance, the functional forms could be added to the causal loop diagram on the diagram itself, as well as whether it's supported only by literature or only by experts, for instance.
Yeah, I'm imagining something like very interactive in the sense that, you know, if you want to see the diagram as a whole, you probably don't want to have all these annotations going on around.
I can show you how we.
Yeah, that would be great.
Suggested, but you're right that
I was also
this is only a very small diagram, so now it looks good. But maybe if it were larger, then.
No, but what I was about to say was that if you think of it as a more interactive thing, you could imagine, like, as you zoom in, you get this information, right? If you're like looking at you want to know about this connection, then you zoom in and you see maybe something to see the references that give you this connection, or you know what I mean?
Are you offering to make such a tool?
Yes, please.
Yes, I just saw some grants that we can ask for people to build tools for us, so that could be an interesting proposal.
This is our example that we use. So in the second part of the paper, which I haven't discussed today, we go through all the different steps of going from this aCLD to system dynamics model. Mm-hmm. And there we use a running example that is, we hope, is so not related to reality that nobody will take offense with this example. So here you see potatoes, worm population, and soil nutrients. And then you see the experts with the prior probability inside of the vote. Uh-huh. And you see the polarity, and these numbers represent functional forms.
Oh, I see. So it's like type 2 function, type 1 function. Is that what the numbers mean?
Yeah, something like
that. Yeah.
Okay. But I think that, So, but Vitor, to turn it around, are you saying that you think it's important to kind of converge to some suggestion on how to do this in a visual way?
I think so, right? Because that's also, I was just wondering that it in some sense it should converge into what people are already used to. And in my mind, I was thinking, like, if you zoom out, you get what you're used to. And then if you zoom in, or maybe you add on some filters or things like that. Because when you're building these things with the stakeholders, of course, maybe, I don't know, it's nice to start. It's nice to start from a familiar framework. But I guess you're right. You're also right that in the sense, in the long run, you could converge to this as the standard. But it's easier to make smaller adjustments than, proposing a whole new thing. Especially with the ands and ors, I think that's really far from many stakeholders. The way they see. I don't think they think that way. If it's a plus that you want to put there, or a multiplication there, and that's what you want to know to implement these things, right? Mm-hmm. Yeah, but super cool. I'll probably use this in my class.
Cool. Thank you. Yeah, I think you're right that we thought, we've already done all of this, so do we now also have to come up with the format? But maybe we should actually try
sounds
to
like something. So
convert
actually, Vitor, if
everything
you
in one.
or anyone else, if you have some suggestions on how to improve the format, that maybe with this one stone we can also tackle that bird.
Mm.
That would be really great. Right, thanks,
Okay.
Vitor. So I'm also getting a question or two questions from the chat. So one is from Peter Isager. I don't know if Peter wants to say it himself or if I should do it.
Sure, I can do it. Thank you so much for the talk. It was super interesting. It's formalizing some stuff I've been thinking about for a while. I was wondering if you can give an example of your own work of how you actually go about translating verbal statements from experts into structural equations you would put in a model, because it seems like a very difficult thing to do in practice to me. I'm just thinking about, for example, if I would go ask clinical psychologists to give me a description of how a causal mechanism between two symptoms work, for example, they will probably describe it verbally, but to translate that into a mathematical equation seems like really challenging. Curious if you have like personal experience.
Do you have personal experience, Rick? I don't have personal experience.
Well, your diabetes project, right?
Yeah, but we did not actually ask the experts in this way that we suggest here. So it was more the other way around, that we propose something and then ask, does this come close enough? And then if they say yes, then we did that. So I think this could be more really to narrow it down, as opposed to saying this is exactly what it should be. Because I think you're right that it's a lot to expect that someone could maybe draw something and that's it. Or so more to say what it definitely not is, to narrow it down.
Cool, thanks so much.
I guess that in the system dynamics model, we can use, we can make stochastic differential equations, right? So we can add probabilities and uncertainties in different parts of the model. So I assume that this kind of qualitative expert description, which could be like an expression on in terms of how much confidence do I have in this, or how much confidence do I have in that kind of statement. I'm pretty sure we can encode that in the system dynamics also. But of course, there's not a one-to-one mechanism to do that. But in general, I think we can do that. We can encode uncertainty or expectations or whatever. Is that what you were aiming at, Peter?
Yes, sort of. So for example, I'm anticipating, I like the idea that you can like start out with a suggestion and put it forward to experts. That seems like productive. But I'm also imagining like sometimes, for example, you could pick up from verbal language that a process couldn't work in certain ways. So for example, that an expert might describe certain, like say I am interviewing a clinical psychologist, they're describing how someone with drug addiction presents to them. And it seems like I could take verbal descriptions of how that patient presents from week to week and figure out, for example, that there can't be a linear relationship between drug intake and proclivity to take the drug again, for example. And that somewhere in that verbal description, there's a possibility to at least narrow down the range of equation types that would explain the relationship mathematically. But how to actually do it is a little bit beyond me at the moment.
I think it's an interesting question. We can probably come up with some kind of toy model for that. So maybe we should have a chat afterwards to see if we can come up with a very relatively simple toy model playing with that idea.
Yeah, I think it's a very important point, Peter. And I think that if I can add, so the crucial part that the causal links aim for is encoding causal links, right? So the question is really down to the question of if you would intervene and change the value of A or the state of A, would you then observe a change in B within the time frame of your model, of your research question? And then, so a description of first I see this and then I see this and then I see this, or I observe a correlation in my patients between this and this, is not yet sufficient to actually put down a causal link, right? And yeah, and it can be that often when you try to zoom into, okay, tell me, will a causal intervention in this lead to a result in this? If then it could well be that typically the answer would be, I don't know. Yes, and then you're in for a very difficult time in the second part of the of the analysis, which will be building the model, because your structural uncertainty will be humongous. But at least it is correct. That is, yeah, but it's very hard to do. Yeah.
Can I hook in on this? So I was wondering if this I missed the first part of the presentation, to be fair, but does this model also include like possible hyper edges between effects? So you're not only, it looked like you have a simple graph, but it could be that, experts, they say, well, there's this thing that interacts both with a bunch of other things. And we have to include those in there. Because I imagine that the function can have any type or form, but the sort of interaction upon interaction in these very complicated systems may be non-trivial to even know for an expert what those would be.
Yeah. Yes, it includes hyper edges. Yes, so okay. Things like AND gates and OR gates was presented.
Can I quickly jump in on that? I also saw that in the presentation you mentioned many-to-one links, and this confused me quite a bit because one of the things about causal loop diagrams is that they're supposed to be very clear and intuitive understanding of the feedback loops, right? And so what I don't understand is why you wouldn't represent a many-to-one link as actually you're sorry, let me rephrase that. If you're adding a many-to-one link, aren't you just then sort of purposely omitting an intermediate step that might actually be important? Like there should be some state in between that gets affected by those two things, and then that causes the joint effect. No.
I mean, I'm not part of the modeling team here, but I could imagine if that effectively you could leave it out, then it doesn't matter, right?
Well, but you don't know, because then something else might also affect that, right? Like if we're saying we're also considering edges that might be absent, then you can't just take out a node and say, oh, this is many-to-one, right? Because I mean, many-to-one isn't actually a thing; it's an abstraction, right? But if we're trying to be not abstract and to actually include all the mechanisms and edges we don't even know about, then we can't just leave it out.
But is
Well,
it necessarily an abstraction? I'm not sure about that, but even if that were the case, you also don't want to. So every causal link, of course, has mediators that you are not including. That's always the case. So if you then think about that, if you don't want to go to certain spatial and temporal scales in for the functioning of your model, even though those would be mediators over there, you could decide to leave them out, and that then also entails this many-to-one causal link, that even though you would need additional things to explain this link, maybe they're not necessarily included in your model, because there's always mediators that aren't there, of course.
But the many-to-one could be something as simple as how many, like from how many sources I get money, right? I get money from my daytime job and my nighttime job, and that adds to my total money, right? That's a 2-to-1.
Well, I would say that is two interactions which are in parallel. So you could draw two edges basically, because then if
Yeah.
I would increase the amount of money on one of the sources, it easily translates
And you're
in a
saying
trivial
that's
way
an
to my
or,
amount,
but
right?
and then you were saying that that is an or, right? Kind of, it can come from this side or that side. But when I represent that in a causal loop, I don't know if that's an or an and.
I think they are separate, as Rick said, because even though so they are not necessarily in interaction. If one changes, then your amount of money becomes higher, even though it doesn't matter what happens to the other one. Whereas with the and the or, you either need both or you need one of them.
The or alternative. Okay, yeah. Okay.
Yeah,
Oh,
so
yeah.
a single link drawn
Yeah.
from, let's say, A to B suggests that there's really a direct causal cause and effect from A to B. So I change something A and something happens on the other side, regardless of something else. If this causal link is conditioned somehow on something else, maybe the polarity or so depends on something else, then it becomes a kind of many-to-one, kind of higher level interaction. Because, and then drawing single edges or maybe two edges or something would be kind of confusing or misleading, because it suggests that there is this path of causality, which there may not be, because there is this interaction that can intervene.
And so would there be anything you cannot capture in this? Like any interaction that would be difficult to go through this process and then not be able to represent it? Because I can imagine, like in biology, you have all these cofactors that mediate certain probabilities of something happening somewhere else. And it's not necessary that if you find some molecule A in a position that it would necessarily be causally related, but it could be a mediation factor to something else. You know what I'm saying? Like they're not, the process could also happen without this mediating factor, but maybe it's more effective.
Wouldn't you still capture it? Wouldn't you still put that into the structural equation in the end, so that you could always represent it by saying, like, are you talking about a factor that by itself doesn't really matter, like, but it, or like a necessary condition that normally is always the same or something?
Yeah, I don't agree with a clear example right now, but I can imagine that you have a sort of cofactor somewhere that by itself indeed is not necessary for the reaction to occur or the causal vector occur, but if it's there, it would be more effective or more likely. And then like maybe that factor is also involved with many other causal processes, and so the diagram would then be quite complex and non-trivial to interpret.
But you can make like a catalyst, right? So something that in itself is not doing anything but just helping the other reaction, so to say, to work. So if that's what you're meaning, you can do that, I guess. It's just part of a regular diagram, right? So something that says, okay, A causes B, and that's mediated by something else as a catalyst, and it can stimulate or reuse. I don't see the problem there, actually.
Yeah, so just as a thought experiment, would there be anything that would be difficult to capture in this process?
That's a very good question, actually.
I'm wondering about that.
Yeah, I think
Well,
in terms of functional forms, we're free to put anything, right? But there is, for instance, the assumption that there's this discrete amount of variables that we place. Like if that somehow becomes a continuous field or something, I guess this way of describing the system would lose its edge, I suppose.
Yeah, it can become very cumbersome for very high order relations, right? So it is still underneath a relatively simple differential equation, the difference equation, I should say. So even though you can, the higher order you can relatively easily express in your aCLD, implementing them in your SD can get pretty nasty, and then you don't see anything anymore. I mean, I guess that's might be the biggest drawback of the whole thing, the higher order interactions.
I had one question about the idea of like preconceived bias in the experts, because to me that seems like also a big issue, right? So, I mean, this is basically theory building. The idea is not to do necessarily a predictive simulation, but something that helps you understand some mechanisms. So do you think about like having different sets of experts to somehow, you write down some axioms or some sort of conditions that must hold, because you have an experimental frame, right? You mentioned this, Loes, at the beginning, that the model has to be designed in a particular condition. It's measuring a system in a particular condition, and typically you're interested in an output measure or a set of output measures. So do you think about like, getting some experts saying that this should never be negative, or this should always be between these values, then having another group of experts design the whole system and then checking those axioms, just about how the validation process works? Because otherwise, most often in complexity, we're interested in things which are surprising and that are not kind of, and maybe you get lucky, maybe that just comes out by the causal loops that they've generated, but more often than not, it's something that you didn't think about. And maybe the data tells you, I don't know. So how does that work in practice?
Well, I haven't discussed that today, but we give some suggestions for that. First, that's related to the structure of the model itself. So before there's any computational stuff going on. So that could be that you present the causal loop diagram, annotated causal loop diagram, I should say, to another group of experts to see whether they agree for a validation, because that's actually the only way, because in theory, all the literature is looked at and you have no other way of validating the topology of the model. And then we suggest to do these validation statements exactly as you say, and we've already done something like that before for one system dynamics model. And there we have defined validation statements that are not about the primary outputs that you are interested in. So they are not about the research question, but they are about these small other things that you could check. So also, for instance, it's a bit like these extreme value conditioning or something like that, condition tests. I mean, so if this changes, then this should happen in this other variable, and then a whole bunch of statements like that in order to test whether it functions as would be expected without just, as you say, looking at only at the output variable of interest.
Yeah. Yeah, and I think that in a way, if a group of experts possess some bias, it is only fair to implement this in the model, right? I mean, the model is not correct; it's a reflection of the common consensus of the experts. So in a way, it is fair.
Yeah, that's what I meant by the theory building, right? So if you can show them why, that's I think that's the biggest power of the model. So eventually, you make them revise the assumptions that they had in some way. But it's better to write that down. So if they write down some axioms or some statements first and then have that come out, then you can show that, this is obviously clearly wrong, or there's something missing.
Yeah, yeah.
But then still, your the fact that you can do sensitivity analysis of the system allows you to pinpoint whether it matters or not, right? So how much does it matter? How much does this opinion matter for the question I'm asking? So you can do this, you know, if you have this large factor of variables and you just differentiate them all to find the Jacobian of that thing. And then you say, okay, well, you know, if you ask that question, then that doesn't matter, but that does matter. And then you can zoom into that opinion, I guess.
Yeah. So maybe a final question I think I see from the chat could be Jing Meng. Oops. So Jing Meng, would you mind?
Yes, thanks. Yeah, thanks for your presentation. That's very inspiring. My question is more like in the combination of the left and the right part of the whole framework, because I know there are many fields where there are a lot of uncertainties even among expertise. So these uncertainties can produce very high amount of combinations in the following computational models. So there's like so many possibilities that maybe is not feasible to try every one of them. And even if we can try every one of them, there is still a lot of parameter calibrating things afterwards. So that sometimes maybe we need to see whether the whether one model can work in the whole range or it can only work in a small part of the whole state space. So I can imagine there would be a really large state space of models to explore. And do you have any suggestions about what the modelers should do in this part? Does it mean that we should not use simulation if there's a lot of uncertainty, or should we just pick one or two of them and go deep into that?
Yeah, no, thank you for your question. That is certainly true what you say. I think what Rick said before is kind of applies here as well. So that the idea is that you then don't pretend that you are certain about it, which is one very important idea behind this. And I think if you have in your head now, as I do, the causal loop diagram that was developed by Jeroen for Alzheimer's disease, I don't think it's feasible for him to quantify this model in one go, kind of. Because, as you say, there are so many links and so many uncertainties, and this is computationally unfeasible. So what could be a suggestion then is to take a subsystem of the larger system and start with this, and then iteratively add different mechanisms to it. But I think it can also be a conclusion, that if there are too many uncertainties, then it's unfeasible at that point in time. So I don't think that you can say, well, if you do this, it will work for everything.
Yeah, thanks. Good point. Thanks.
Yeah, although I guess it would be or could be possible to do something like sensitivity analysis and figure out maybe what type of knowledge or data that maybe domain experts could try and gather would give us the most of the largest reduction of uncertainty, right? So then the outcome of the modeling approach will not be an answer, but it will be, or not an answer to the research question, but an answer to the question of how can we get closer to the real model.
Yeah, that's also a good point. Yeah, thanks.
So I think, all right, then I propose that we leave it at that. We can of course still have our EOS drinks, although we're not in EOS. So that's a very difficult thing to do. But so thank you very much, everyone, for being here. And thanks a lot, Loes, for this very nice presentation. I think it spurred a lot of response also in the chat. So,
thank you.
And
thank you very much.
So thanks,
Have
everyone.
A nice weekend.
Have a nice weekend.